So in 3.4, we learned two really important rules on how to deal with product and quotient functions. And in 3.7, we're going to learn another really important rule on how to deal with composite functions. So we are skipping a couple of sections, but we will go back and cover 3.5 and 3.6. But I like to cover product rule, quotient rule, and chain rule all together. So in 3.7, there's only one new rule, and it's the chain rule, and it's how we take derivatives for composite functions. And again, there may be a way to avoid this using algebra for some of them, but not all of them. So you should have learned about composite functions in algebra class, and that is when we have one function plugged into another function. So a composite function we usually learn the symbol with that little O symbol. We're really not going to use that symbol at all here in calculus. But we see that here G is plugged into F. G is plugged into F. So if we see that one function is plugged into another, and we're trying to take derivatives. So some examples of what this might look like, and we're not going to take derivatives yet. But if I'm trying to take the derivative of x squared minus 9x, and the whole thing is raised to the 8th power. Now, I wouldn't want to have to write that out 8 times and FOIL it all out to do the algebra to fix that. We know how to take the derivative of things to the 8th power, but that's only when it says x to the 8th, not when it's an entire function written to the 8th power. So this is considered a composite function because it's an actual entire function of x to the 8th power. So there is an inside function, and we're going to talk about this a lot, and there's an outside function. Another example, when we start looking at trigonometry in the next section, anytime there is something plugged in to the angle, so say the sine of 5x, that's considered a composite function. So the 5x is the inside function, and the sine is the outside function. And we've seen lots of derivatives so far with e's. If we want to take the derivative of e to the negative x squared. We've talked about the derivative for e to the x, and then also at the very end of 3.4, we've seen the derivative for e to the kx, where k is just any real number, so e to the 5x, e to the negative 2x. But e to the negative x squared is a whole different beast. So the negative x squared is plugged in, so that's our inside function, to the e function. It's plugged into the exponent of an e function. So we say negative x squared is the inside function, and the e is the outside function. So it's going to be really important to be able to identify the inside and the outside, because that's kind of the basis of how we do these derivatives, is the derivative of the inside and the derivative of the outside are going to be combined. Okay, so composites are where we have one function of x plugged into another function. So our book uses kind of two different notations. I'm not a huge fan of telling my students multiple ways of doing things. I think it just makes it more confusing. But because of the way this homework is set up, they want you to identify the inside and the outside, and they like to call the inside the U. So for the sake of making the homework a little bit easier, I'm going to try to do this lecture similar to the way the homework is set up. And hopefully it'll make the homework a little bit easier. So technically, the chain rule says if you want the derivative of f of g of x, this is my preferred way of writing it, but then I'm going to show you another way. First, you're going to do the derivative of the outside function, which is the f. So you're going to do f prime, but you're going to leave the inside alone. We're not worried about that right now. Whatever is on the outside, you're going to do whatever the derivative rules are for that, but leave the inside stuff alone. And then we're going to multiply by the derivative of the inside stuff. So right at the beginning, you have to be able to identify that it's a composite function and identify what the inside and the outside are. So if you see it in the homework, they actually call this version 2 of the chain rule. I don't know why they decide to talk about two different versions, but they do. And a lot of the problems in the homework actually use this first version. They say that dy dx, which is just another notation for derivative, can be broken apart into two pieces. They say it can be dy du times du dx. So dy du is the derivative of the outside piece, and du dx is the derivative of the inside piece. And they like you to identify the outside and the inside and do like a substitution and actually separate them. So that's where the U comes in. That's where they introduce the U. And actually in some of the homework problems, they introduce this U. So I want to do a couple of examples and show you how exactly they do that. And they call this version 1 of the chain rule. So if you see any reference to version 1, that's kind of what they're talking about. Or even if you just see them using the letter U, that's what they're talking about. So I wrote one earlier, x squared minus 9x to the 8th. And I'm going to show you what they're talking about with splitting up the dy dx into a dy du times du dx. So what they want us to do is rewrite the outside and the inside, kind of like how we rewrite our product rule and our quotient rule as two separate functions like a f and a g. Only this time we're going to write it as a a y in terms of a u and a u in terms of an x. So what they do is they rewrite the inside function. The inside is equal to u. So my inside, and almost the inside is usually easy to identify because it's got parentheses around it, or it's inside of a square root, or it's inside of a denominator, or it's inside of an angle. So it's usually quite obvious that it is inside of somewhere. And most often it's inside of parentheses. So the very first thing, we're going to let the inside of the composite equal u. So I've got u equals x squared minus 9x. If I do that, then I can rewrite this problem as u to the 8th. And that's my y. So I've got y in terms of u, and I've got u in terms of x. So if you look back at what we had up here, I'm going to be taking the derivative of y in terms of u, and I'm going to be taking the derivative of u in terms of x, and multiplying them together. So I'm letting the inside of the composite equal u, and then I just wrote what I had left over. I replaced that with u, and I wrote what the original problem with u in there is just u to the 8th. That's my y. So take each derivative. So this is going to be du dx, because remember, we do the output variable in the top, the input variable in the bottom. That's 2x minus 9. Do the output variable in the top, the input variable in the bottom. That's the power rule. That's going to be 8u to the 7th. Now when we write our answer, we want it all in terms of x. Oops. So the next thing I did here was I find du dx and dy du. We need to replace the u in dy du and write our final answer. And our final answer is just our two derivatives multiplied together. But I don't want my final answer to have u's and x's in it. I want it to just all be x's. So this one's fine, it has x's. But this one I need to rewrite. So wherever I had a u, I want to go back and replace what we said u was. So really, dy du is going to be 8 times x squared minus 9x to the 7th. So our final answer is dy du times du dx so 8 times x squared minus 9x to the 7th, and then times 2x minus 9. That took care of the derivative of our 8th power, but it left the inside alone, and then it multiplied by the derivative of the inside. So if you look back at version 2, it followed the same exact rules. I think version 2, I think, is a little bit more straightforward. It's just the derivative of the outside piece times the derivative of the inside piece. The way that the homework problems are set up, and I didn't have much choice in this, they use the U a lot in the homework, and I didn't want that to be confusing. So they ask you a lot, what's U equal to, what's U equal to. So I just wanted to make sure I touched on that, and you understood that. So that would be our derivative. The derivative for e to the x cubed minus 5x. E to the x cubed minus 5x. We're going to let u be equal to the inside stuff. And we're going to replace and let y equal to what we see when it's replaced. So y is equal e to the u. We're going to take the derivatives now, du dx, because u is written in terms of x, is going to be 3x squared minus 5. dy du is just e to the u. But for our final answer, we've got to write that back in terms of x. So if we plug the u back in, it's e to the x cubed minus 5x. And our derivative is just, our final derivative is just these two individual derivatives multiplied together. So 3x squared minus 5 times e to the x cubed minus 5x. The derivative of the cubed root of 5x squared plus 2. So u is going to be 5x squared plus 2. That's the inside stuff. And if we replace that, all we're left with is y equals the cubed root of u, which we can easily take the derivative of if we rewrite cubed root as a power. So du dx is 10x. We're going to want to rewrite this as u to the 1/3 so that we can find dy du, which is 1/3 u to the negative 2/3. And once we get that, we rewrite it in terms of x. And then our two individual derivatives multiplied together are our final answer. So we have 10x times 1/3 times 5x squared plus 2 to the negative 2/3. And we should clean this up a little bit. We should always try to clean up negative powers. That exponent of negative 2/3 actually means three things. The negative means it wants to be moved to the denominator. That denominator of 3 in the exponent means it's under a cubed root. And that numerator of 2 in the exponent means it's squared. So we're going to be creating a fraction for our final answer. Only the 5x squared plus 2 has that negative 2/3 power. So that's the only thing that's going to be moving down. The 10x is staying up. The 1/3 means that 1 in the top multiplying by 1 doesn't do anything, but the 3 in the bottom. And this is going to be cubed root of 5x squared plus 2 squared. That's probably the nicest way we could write it. So it's in the bottom because of the negative power. It's in a cubed root because of the 3 there in the denominator of the exponent. And it has a square on it because of the 2 in the numerator of the exponent. And let me also show you one where we have to combine possibly some product rule, quotient rule, or chain rule. But other than that, the chain rule is the only thing in this section. Let's do the derivative for 3x over 4x minus 1 to the 5th. This is one kind of like we did back in section 4, where you may see several different rules you could apply, and you might be confused as to which one you should apply first. But what I encourage you to do is look and see how you can label things. Don't jump to any conclusions. Don't be scared to mess up a lot of paper. You're not trying to conserve paper here. If you need paper and you can't get any, let me know and I will get you paper. This, no matter what is inside the parentheses, whether it's a single function, whether it's a product of functions or a composite of functions, this is a composite function. You have to use the chain rule. Only a piece of this function is a quotient. So overall, this function is not a quotient. Only a piece of it is a quotient. So you couldn't separate this function into just a numerator and just a denominator and take care of all of the pieces necessarily. That still wouldn't take care of the 5th power on the outside. So you want to find a way to break down this function where all pieces get taken care of. So you can't do that with the quotient rule. You can't say f is the top, g is the bottom. You haven't taken care of the 5th power yet. So we don't want to start with the quotient rule. We want to start with the chain rule. And the chain rule says u is the inside, the entire inside. And when we replace that, we let y equal to, so replace the entire inside with u, and then that's going to say u to the 5th. So y equals u to the 5th. So chain rule would take care of the entire thing. Now, just as an intermediate step, when I have to find du dx, in the process of finding that derivative, I'm going to have to do the quotient rule because my u is a quotient. Now that the 5th power is off of it, I have to do the quotient rule. So now if you want to, you can split u up and say, well, f of x is 3x, g of x is 4x minus 1. So f prime is 3, g prime is 4, which means du dx is going to be, remember it's f prime g, so it's going to be 3 times 4x minus 1 minus fg prime, so 3x times 4, all over regular g squared. So just the process of taking the derivative of our u, just the inside, is a quotient rule. And we should clean that up a little bit. So du dx, that's going to be 12x minus 3 minus 12x over 4x minus 1 squared. And those 12x's cancel. So du dx is negative 3 over 4x minus 1 squared. And then dy du is 5u to the 4th, but we need that rewritten in terms of x. So dy du, just plug back in what we said x was going to be. It's 5, 3x, 4x minus 1 to the 4th. And we'll take our two derivatives and multiply them together for a final answer. So we get our final answer here is negative 3 times 4x minus 1 squared. And then we've got 5 times 3x over 4x minus 1 to the 4th. And just like with the rest of them, there's a few things we should do to clean this up. Be really careful because this fourth power applies to everything inside of the 3x over 4x minus 1. It does not apply to the 5 though. So we can go ahead and multiply the 5 times negative 3 is negative 15. We are supposed to raise that 3x to the 4th power. I do have a 4x minus 1 squared and a 4x minus 1 to the 4th. So I went ahead and separated those because I saw that I had lots of them in the bottom that I could put together. So 3 to the 4th power is 81. I'm going to go ahead and just multiply this out. I did see in the homework that a lot of them were multiplied out. So 81 times negative 15 is negative 1,215 x to the 4th. And in the bottom, we're going to have a total of 6 for x minus 1s. So we got 4x minus 1 to the 6th. So that is our final answer for the derivative. And we ended up having to do a quotient rule inside of a chain rule.